Okay, great. Okay, so the last part of today's workshop will be about Dorado. Who here has heard of Dorado? Oh, that's good enough. Hopefully, we can excite you to use Dorado also for your work in the future if you have never heard of it. Sorry? Oh, yes, sorry. Of course. I'm Muriel Brückner. I'm assistant professor here at LSU in the civil and environmental engineering and coastal engineering. And the reason why I'm here is because I did my postdoc at UT Austin and I was paid by the Delta X project. So that's why I'm happy to give the presentation today about our work with Dorado and do the tutorial. So hopefully you can all work with Dorado after this. I also put Antoine on here, so we did put this all together. So this is just not just my doing what I'm presenting here, but Antoine and I worked together on this. So Dorado is a Lagrangian transport model. And here you have an example of how particle transport would look if you use the data we're going to use in a second. And compared to other models, Dorado is basically a more simplified way of modeling particle transport, which is called reduced complexity approach. Somebody has heard of a reduced complexity approach before? So basically, it's simplified in a way that you have a cellular routing scheme where you just route particles from cell to cell based on a stepping on that is defined on different set of rules and how the particles will move through the domain. So that's different from purely physics-based models that really calculate transport of particles through the physical equations and empirical equations. And so basically, if we use this reduced complexity approach, we save a lot of time and computational energy. So we can actually model really large domains and particle transport through those domains compared to if we use, for example, Delft3D or a more complicated model. And so this is just an outline on how the path would be calculated. That's called the weighted random walk. So basically, if you have a particle in a cell, it has 8 options to move into the surrounding cells. And so how do we decide how we'll move there? That's based on 2 factors. One, where does the flow actually go? So what's the flow velocity vector? And what is the resistance of the downstream cell to the particle actually entering it? And that's just a background for you to understand how we actually define how the particles will move through the domain. And so there are 2 equations. I'm just going to show them briefly because we will look at the parameters in a second that define those equations. One is the transport direction, F star here, and that basically is the transport direction of the flow that the particle will move in. And so it depends on the surface gradient of our water level and the inertial component, which is basically the discharge. And we can control which of them basically dominates our transport by having this weighting factor gamma, which I circled here in red. So basically, we can define this parameter in the models to determine if we want our particle to depend more on the water surface slope or on the inertial component. And the other more important factor is the weighting factor, W, which is actually the resistance of the cell. So basically, we compute the flow direction, and then we weight our particles based on a probability distribution. So how likely is it that our particle will actually enter one of the 8 cells that we do have? And that one depends on the water depth. So here we have the relative weight on where the particles will go based on a local water depth and the size of the cells. And this illustration here in the bottom actually shows you that we can modify this dependence on the water depth based on a parameter theta here. So basically we have theta set to 0. That means we're looking at water. So the water will go into all cells just based purely on the water depth. If we increase or reduce theta, then we actually have a stronger or lesser dependence on the water depth of the particles. And that is defined here as the power function of the water depth. So what I'm trying to say is that if we modify theta, we can actually control where the particles are transported in the water column. And to illustrate this in this figure, Basically, if you think about very small particles, you would expect that they float at the top. If they're negatively buoyant, they might even be like plastic particles or something, they would float at the very top. And if you have larger particles like sand, they would float lower in the water column because they're more on the bottom. And that is basically the assumption behind Dorado. So basically this theta controls where in the water column our particles are floating. And so depending on how we set this, we can define different types of particles. So it can be sediment, it can be sand, it could be wood, whatever you're interested in. And then you can see the flow path of the particle depending on this water depth. So that was all the theory we had. So just an example here how this would look. So we have here again our animation, and then on the right-hand side, we do have the colors depending on the theta. And so this is the same simulation like here with different types of theta. And you can see that if you have a high theta, which is yellow, it actually reproduces particle transport in the channels. While if you have a lower theta, particles are more likely to go on the wetlands and into the higher intertidal areas. So that's how we can actually use the theta to reproduce the transport of mud versus sand, etc. And so this is useful because we want to know where the flow paths are and relative to what the particle properties are. We want to maybe know how likely is it that we get sediment in a certain area, depending on the sediment. So if we think about wetland nourishment, for example, we want a lot of particles. So which type of particles are more likely to go into the wetlands? How long do they stay there? So how likely can they deposit, etc. And that is, of course, important for deposition, nutrient uptake, and algal bloom, etc., and those type of things. And the reason why I'm saying this is because people are often very critical when it comes to these reduced complexity models, but they are very efficient computationally, and they reproduce realistic patterns that we see. So they're actually really useful to understand general system behavior and where our particles will go in here in the Mississippi River Delta. So I'm just going to show you a couple of examples, and then we dive into it. So basically, those examples are from the work of our group or other groups at LSU, and we're going to do similar things now in our tutorial after this. So one thing we could ask is, how can we nourish our wetlands because they're drowning? So what types of particles will enter wetlands, and what are the conditions they enter the wetlands? And so that can be controlled by something that's called channel island connectivity, because if we have high channel island connectivity, we get a lot of particles into the island. If we have low connectivity, we get a lot less particles into the islands. And so I'm just showing you results of two simulations where I used the theta to parameterize sand and mud in Rex Lake Delta and looked at two connectivity scenarios just to illustrate how this would look. And so based on these graphs here, I used 1.25 for the theta of mud and then 2.0 for the theta of sand. So we have a very high theta for sand and a little bit higher than water for the mud. So we get the two different transport modes, one in the bottom of the water column and one like not so much in the bottom of the water column. And so these are two scenarios, and the yellow dots are the sand and the brown dots are the mud for the different connectivity scenarios. So you can see that depending on the connectivity, you already have a different distribution of those two particles, but also based on the particle properties, you can see, for example, here in the right picture, which is the low connectivity, that a lot of the brown particles are actually entering the wetlands from the tides. So we can actually control where the particles go just by changing the theta in the simulation. And so once we had the simulation, we would like to know how many particles actually went into the different areas. So we can plot something that we call a nourishment map, which we're also going to do. So that's the relative number of particles that you get into an area. So if we have the mud on the left-hand side, we see that that nourishes a large area. So all of the particles are actually entering the wetlands, while for the sand, that's not really the case. So that's one of the things that you could be doing, looking at how many particles of all the particles that I have are actually entering a certain area. And then the other thing I'm going to show you is the residence times. That's work by Katie Turner, who's also here in the room. That's on a lake here in Louisiana. And she's interested in how do the particles actually leave this lake if you have different openings of the different river discharge and different openings of the spillway down here. So basically, where do the particles go if you have different scenarios? And in this case, we have the particles seeded everywhere in the domain at first, and then we see how they leave. And so that's her simulation. So here we see that we have the tides on the right-hand side and the bottom going in and out, and the spillway is open, basically pushing the particles out. And so we also have a river coming from up here. So the particles are actually leaving the domain, and then we can calculate how long does it take for these particles to actually leave? How long is the exchange rates of these particles? And those particles here are water. So the theta would be 0. So you can look at how long would the water actually stay in the system before it's exchanged. And so in order to assess this, we can calculate something that's called the exposure time, which is basically the number of particles that remain in an area, and then identify different flushing scenarios. And these two maps basically show the exposure times of the particles. So you can see that the median exposure time, where the dark red areas are more on the western side of the lake. And if you look at the maxima, it moves to the northern side of the lake. And then we can plot this as a cumulative density function, which is this lower plot here on the right. And then we can assess how many days 80% of the particles are actually in the system, or 60%. So we can quantify how fast do our particles leave the system just with the particle tracking. And so, yeah, this is Antoine's simulation. That's just an illustration on how a large-scale simulation can be done quite efficiently. So this is a large model of the Mississippi River Delta, and he seeded the particles up there at the top. I'm not sure, can you see that with the light? Yeah. So basically, he sees the particles up there at the very top, and so they move through all these different channels down into the Atchafalaya River and the Atchafalaya Delta, and also over towards the side, towards Terrebonne Bay. So it is easy to model particle transport very fast on these very large-scale domains compared with proper sediment transport models. Okay, so that's hopefully convincing enough that we should do this now. So here, just the workflow in Dorado, we're going to move through it together. So basically, there's 3 steps. Dorado is written in Python. So it's basically Python packages that you can or have already installed on your machine. And we have different codes that actually have all the functions that we need. And you can actually check them. So it's very easy to access them and look into them. And if you are a Python user, you might want to change things. It's kind of a very user-friendly, I would say. And so 3 steps are: you first need to initialize the parameters in the model. That's done in a class that's called particle track. And then we initialize the particle parameters, which is also done in particle track. And then we simulate the particle evolution using a code routines. And so for the initialization of the model, we need parameters like the grid cell length, and we need the flow field. And basically, Dorado can be put on any flow field that you have. So here it is ANUGA, but if you have a Delft3D flow field or any other model, you could put Dorado on that flow field as well. So it's really versatile and can be used with many different output data. But we need a flow field to be able to run the particles. And also in this particle track, we will define the theta and the gamma, which are these 2 parameters in the equations that I showed you that will modify your simulation. And the second step is then to define your particles. And that's basically the number of particles and where they will be seeded on your domain. So we're going to do all of this in a second. And then there are some other options that we can take that you're probably going to be seeing in a second, but you can modify those functions as well. And then the last step would be to define how long do we want to run our simulations or how many iterations, and then start the model run. And so I find it very useful that these Python codes are actually on your computer or in the documentation if you want to have a look. So if you have a question about how one of these functions works or what parameters you might be able to adjust, you can always go to the codes and look at them. And so for me, I have a Windows machine. For me, these codes are usually stored where your installation is. So I have this on my C drive. So if you want to have a look at where your codes are, I'm in the environments of my Miniconda that I installed, which is my Anaconda version that I used. And then at some point you find Dorado. And here you have all the Python codes that I was just referring to. So you can have a look and just open them to see if you to see what they actually entail. Okay, that's all I had. Are there any questions before we get started? Yes. I guess that's Antoine's model. He's calculating. We get back to you in a second. So you can run it on several cores. So you can parallelize it. I haven't done that. I personally ran the simulations with the different connectivity scenarios, which are on Wax Lake Delta. I run them on my on one core, but it's a computational computer. And I think it really depends on the number of particles. That's like the main determinant. So if you have 100 particles, it might go fast. If you have 1,000 particles, it might take 20 times longer. So I would think that my simulations for 2 weeks of hydrodynamics would take 10 hours for 1,000 particles. Yeah, that's a really good question. So they are depending on buoyancy. So where the particles are transported in the water column is actually approximated by how buoyant they are, so where they're transported in the column. So in that sense, they do have a mass, but you don't define a mass in terms of particle diameter directly. You can calculate a theta through that, but basically the main parameter in Dorado is the theta that controls the size of the particles through adjusting where they're transported in the water column. Was the second part? Oh yeah, no, you cannot. This is purely like a Lagrangian transport, so you just track the particles where they go. You don't have particle-particle interactions. You can not just with the normal Dorado implementation, but you can assume settling through calculating what size they would have depending on the theta that they have. And then if they stay in an area for very long, you could estimate how that they would deposit. Yeah, thank you. So Dorado, it can be found, can be just installed as a Python package through Git or through Anaconda, like we did. The products.
The ultimate output for the DAC purpose would be to have a sediment deposition rates.
Yeah.
Right. So for the DAC, I'm guessing no. Because we have one already.
So the answer is no, the Dorado products will not be stored at Ornell.
Okay.
But everything is open source, so you could.
Yeah, exactly. So I guess that anything that will be published will be open source in the journal or in the nodal after publication, at least. Okay. Antoine, did you find out how many particles? 36,000 particles. How long did it run? One day on the supercomputer. Mhm. Yeah, so that's a good point, actually. So Dorado is put on the flow field, but the flow field is already solved. So you don't compute the flow field while you're calculating Dorado. So that's why it's also faster, because you have already done the hydrodynamics before. So then you just put the particles on top of it, basically, and then they just spread. Okay, so just show you one more time that this is the folder where the Dorado is installed. And so here you have the different codes that you can have a look at. And I already showed you the two most important ones, which is particle track and particle routines. Oh, sorry, routines, not particle routines. And particle track has basically is the main wrapper for running the Lagrangian Walker model. And the routines is kind of like another code that provides more functionality to actually easily run Dorado. But so we run Dorado the same way as we did with ANUGA. So if you have installed everything, then you have to open your Anaconda prompt. You activate your environment, and then you start Jupyter Notebook. And so that will give you the folder structure. So you should know where your results are stored. And so ideally, you have the results of your ANUGA simulation now together with all the other codes. So mine are stored in documents. So I have my folder here. I downloaded the files from ANUGA that we just did in the previous run. And so in this big folder, so the codes are there. That's what you mean? Or okay, not for me, but that can be solved. Would it look like this? Ah, the sediment thingy.
Sediment transport for Dorado.
Can you dictate it for me, Antoine?
Sediment transport underscore Dorado. There's a capital T. Yeah, and capital D.
Like this?
This morning it has everything. Yeah.
So it will be in here,
Yes.
like this. Okay, so it should look like this. This one, you mean? Yeah, I'm probably going to run into issues.
So yes, Jupyter Notebook may not work. It might have to be lab if you're using the environment from before.
Oh, yeah. Okay. Okay, so I'm going to navigate to the folder where the Dorado codes are. So there should be two scripts, example 1 and 2. First one is steady flow. That's just an example to get you acquainted with Dorado. And in the second example, that's the unsteady simulation that you just did. And then you can implement Dorado into your own simulation. So if I open this one, it's the same as we did in ANUGA. We have our script with the different coding sections and run the run the codes. And so basically the first one is just to get some output of another ANUGA model that was run with the steady simulations, and then implement particles. So we run the first command. That's just to set the path. You can see here, this command will give you the working directory, which basically means the directory where this script is stored. So basically here you can see I printed. This is where my scripts are stored. And so everything that I load into my simulation will be relative to the working directory. And so from Dorado, this is example data from the tutorial website of Dorado. So that data should be stored locally on your machine when you install Dorado. So they will always provide this tutorial data. So you can import the data. This is just the output data of an ANUGA simulation, and then it will give you the water depth of the simulation and the discharge data. So we have our flow field. That's our step one. We want to have our flow velocities, etc. The next step would be to then establish the model parameters. So this is the particle track class that I was talking about earlier. And this particle track class will define your model parameters. And so you need the water depth or the discharges to get your flow field into your model parameters. So if you run this part, you will have defined your parameters here, and then you're good to think about the particles at the next step. So, yes. Yes.
On 3. Choose, yeah. And then the Dorado. Sometimes it's
That is a good question. I would think you can of course increase the theta to get it to the bottom, but you would not have the typical motions of bed load with saltation and just jumping of the particles over the floor. So in that sense, the behavior is probably more appropriate for suspended sediments. Thank you. That's a good question. Okay. So here we now have our model parameter. Now we do our particle parameters, again with the particle track package and the particles function. And so it will output here tell you a little bit what you defined. Because we didn't define the theta or the gamma, which is the two parameters I mentioned before, they will just go to the default, which will be water. And there's also diffusion coefficients that you could define depending on how your spread of the particle of your particles is. But basically, that will be all predefined if you don't give it any values. Yes. So I think the diffusion coefficient was established to account for the fact that particles are routed in the cell centers. So when you route one particle to the next grid cell, it will be routed to the center of the grid cell. And depending on how large your grid cell is, that's an assumption because the particle might not go straight to the center, but go a little bit around and then end up to the center. So actually the way would be longer in reality of the particle. And that's what the diffusion coefficient should account for, to add an extra length of walk of the particles from the grid cells. Okay, so we define our particles, and then we can run our model using the steady plots command, which is in the routines Python script. And then you will see that you have this percentage that goes through calculating the particle transport. And here we define 50 particles, that this is this number here. So you could also set that higher and you will experience how much slower the model will get. So that's a good exercise. And so this is our domain, where you can see we did now 50 iterations and the particle is routed down here. We can also animate this using another function, which is called animate plots, and that will cause an animation. And so you will find all of this in your folder where you have, in your working folder, where your scripts are, you will see that it created a steady ANUGA example folder, and that's where all your output is stored. So if you double click on it, you will see your animation that we just created. Should look like this. And it will also give you all the other time steps. So if you go to figures, you will see it will actually give you an output for every iteration that we did. Okay. So another functionality that you could be doing is to look where the particles actually went, which is called the particle travel path. And there is another function here that you could be using, and you can choose different particle IDs, basically. So depending on the number of particles that you ran, I have here particle number 10, 20, 30, and 34, kind of random, but then I can run these particle paths and it will actually show me where the particles went over the time of the simulation. And you can do this for all of your particles and then see the different random walk ways. So if you want to, you can play with this, set different particles, just see where the particles are going and try to kind of reproduce this with maybe a different simulation length or different parameters. But how is the feeling in the room? Are people already like far ahead of this? Should we move to the next one? Would you like some more time? Everybody who would like to have more time, maybe raise a hand. Okay, nobody raised a hand. So then I think we move forward. I guess we all got it. Yes. In the, you mean in this one? Yeah. Oh yeah, you can, that is true. So you would need to find, you would need to set a params theta and then define it here. Yes. Oh yeah, that's a good question. That is the starting point of the simulation. Yeah, so that's basically the initial starting point, and then you run the particles to the. Exactly, initial, basically the particles pop up, that's the 0.
Yeah.
Sorry, I also wanted to clarify, so here you define the 50 particles, and here you define the iterations, both 50, so, but it seems like people are willing to move forward.
Is anyone able to animate that has a PC? Okay, so some people are missing the movie writer, so the animation won't work, but it still runs, so.
So the animation just takes forever to be produced?
It's missing the FFmpeg driver thing. Yes, so yeah, if you want the animations to work, we can work on that. Try that, yes. Okay, yeah, so maybe try seeing if the file is produced or not.
Ways to customize like the bit rate or like the frame rate for the animation. It's like 50 time steps, but it's not animating like skip song.
It skips some.
Like it's only, mine only made like a 10-minute video and it's like, or 10-second clip and it's like time set 0, 20, 24.
That's a good question. That's weird. Honestly, that will be a moment where I would look into the code. I'm not entirely sure now. So the code would be in the routines wrapper and called animate plots. So you could go in your routines wrapper and then look for animate plots.
Yeah, so you'd have to change it in the source code. Not when
But
you.
it doesn't seem to give you an awful lot of options here. So was the question that the interval that it's saved is not regular, or that the window frame should be different? Hmm. I honestly don't know why that would be. Does it, so I had that with another Python animation that I did once, and then it would pick output 2 before the output 20 because it would look at the numbers of the names of the output. Could that be the problem? Okay, so it's just a player. Okay, great. Yeah, but this would be an example where if something was odd or I wanted to change it, I would go into the wrapper and then see what happens. Okay, so how are we feeling? Are we ready to move on? Okay, great. So the next script will be example 2, and that will be about the results that you just produced. So basically, you're going to have your domain and your model output, and then you can see the particles. And so you need to set the paths here, which for me I will need to change them quickly. But you need the model data path, which is where you have your model output that will be the shape file that you produced. And then you have the ANUGA output directory, which is where your ANUGA output will be saved. And that is this SWW file that you produce with your simulation. So just make sure that these two are leading to the folder where you save those data. Is that clear? Okay, so I need to quickly fix this because I had to rearrange my folders. Oh. So I would, because I'm here and I want to go one folder back to this one. I would have this. Oh. Right?
Yes, I think so.
No. Don't just point to the cloud directly where it's what we generate.
So I downloaded that data. It's just called for lab because that's how I downloaded it. But it should be leading to the data locally on your computer if you have it. Okay, so if you have set your path, it's actually quite intuitive. We can define the theta here, and then we have an output folder that is created. So you can actually run now several simulations with different theta and see where the particles go and compare them. And each of your simulation will be saved in a new output folder that you will find under your parent directory that is called nourish and then your theta value. So if you have a theta of 1, it will be nourish 1. I might have it here just to show you. So it creates a folder, nourishment analysis, unsteady, and then in here you find the different scenarios. So I just ran one here. This is what I ran. And so if you run different simulations with different thetas, it will create different folders, and those you can compare. So feel free to choose a theta that you're interested in. So remember, 1 is water. Everything above 1 is something that's transported below, lower in the water column, and everything smaller than 1 will be something that's higher in the water column. And it will actually print out where you will find this folder as well, so everybody can find the output data in the end. And so first we load the shapefile that we produced into our domain. And then we need our ANUGA data. So our ANUGA data is in a netcdf file with the SWW extension. Here's a command just for you to inspect what is written in this file. You can find different metadata here at the top, and then you have basically the grid variables. So basically, we'll tell you how many grid cells do you have. That's the number of volumes, different vertices, number of points, etc. And then you have different variables that are stored in your ANUGA output, which will be the coordinates, X and Y, the different cells. You have friction here, bed elevation, etc. So we can call all of this output from our ANUGA and then open it in our Dorado. And so one thing that's required for Dorado is to have the lower left corner of your grid as a coordinate to know where your grid starts, basically. So the Dorado grid will always be oriented to the lower left corner. This is why we extract the lower left corner coordinates here. They are also written here in the metadata, so you can actually also inspect them here. And so the next step would then be to actually load all the ANUGA data to use in our grid cells. So now we just inspected the ANUGA output, but we want them to have the values that are in the grid cells. So ANUGA provides a function to do that, which is called getCentroids, that will actually import all the data and automatically put it on the cell center of your grid. And that's important because Dorado runs also on the cell centers. We run this. It will import the ANUGA output as the SWW vaults, and then we can query some of the variables that we need. So one would be the simulation time. We want to have our grid, which is X and Y, and then we want to transform our grids into an array or a list of coordinates. That's the format that Dorado needs. So everything we're doing now is basically importing our output and then making it ready to then translate it into Dorado. Yes. Oh, it's a break time. Great. Yeah, so I'm in the middle of a script, so that will take longer than the break, I think. So we can just have a break. Are there any questions before we go into our break? Yes. Yeah, that's a good question, and there is a stochasticity in because it is a random walk. that a weighted random walk that basically gives you a probability that a particle will enter one of the grid cells around the seeding point. So for each particle, that probability will be the same, but you basically choose randomly one of those probabilities to actually route the particle. That makes sense. So basically you have the grid and you first calculate the probability distribution based on this weighting, and then you calculate the particle transport. No, yeah, sorry, that's a good question. So the question was if the grid cell location in the lower left corner is related to this. So the left corner is needed to define the location point or the starting point of your grid. So that's just the grid. That has nothing to do with where the particles are routed afterwards. So the particles are always routed relative to where they are. So you start in a starting point, and then there's a probability calculation on where the particle will go. They will move to the next cell, and then you have the same thing going on again. Great. If there are not any more questions, then we have a break. How long? 10-minute break? Oh, that's a great reason to have a break for those who are here. Okay, we start in 10 minutes. Let's say at 35, that's 11 minutes. That makes more sense. And for those who are online, you can also feel free to keep trying things. So I hope everybody had a good break. We have 1 more hour. Oh, 2 more hours. Well, we have 2 more hours together, if you want to. So we were in our second example, the unsteady Dorado. We imported our data that we produced with our simulation in ANUGA. We created a grid, or we extracted the coordinates for the grid, sorry, and now we have to construct a grid. And so the reason that we have to do that is that ANUGA is unstructured and has these triangles, this triangular grid, but Dorado does only run on a rectangular grid, actually squares. So we need to translate our grid. Basically, we have to produce a rectangular grid and interpolate our data onto that rectangular grid to then run our particles. In order to do this, we need the coordinates and we need our grid sizes. This is really your choice. I use here 25 meters, which I think is a good compromise between having accuracy, but not taking forever to run particles. But of course, the smaller you make the grid size, the more accurate your predictions will be, or your simulation might be. So I'm just keeping it here at 25, but it also depends on how large your grid in ANUGA was. So if you had a very fine grid, you might want to have a finer grid size here, etc. So just define our grid size here. And now we interpolate our data onto that new grid. And to do that, we are using a function from the particle track again that is called unstruct to grid. And that function will allow you to basically transform an unstructured grid to the rectangular grid, as the name suggests. And for that, you need your coordinates that we defined before. You need a quantity that you want to interpolate on the grid, which here is the elevation. So I extracted the elevation up here from our output data. And then we define our grid area. That is our polygon of our shapefile from our ANUGA simulation. So if you remember, we imported our polygon up here. That's the polygon you created for your simulation in ANUGA. So basically we cut the grid to this polygon. And then we get a variable bathy, which is then the bathymetry on the new grid, cropped to our domain polygon. And if we run this, I print here the shape of the bathymetry, so that will be the shape of our new grid. And we can use this command here for all the quantities that we need to actually run the model, which will also be our flow field. But we can use a hack, which is saving this command as a new variable, myInterp, which will be basically saving this step as a function, and then you can run this function very easily one more time without rerunning the whole thing again. So it will be a faster way to actually interpolating everything on your grid. Our grid is not that large, so it might not make such a large difference here, but if you have a large grid, then this will save you some time. So we have our bathymetry, and now we want our water depth, our water level, and our discharges to also be on the bathymetry. So we first extract them from our output data. And then oh yeah, sorry, I was shortly confused. But so we extract them, but we interpolate them data and later in the loop because we have an unsteady simulation. If we had a steady simulation, it means our flow field is always the same. So we only have to interpolate those once, the flow field, because this is one flow field that we reuse over time. With the unsteady simulation, the flow field changes every time step. So we need to update and interpolate that flow field every time step in a loop, which we do later. So I forgot about this for a second. So here we just extract the data. And then we move on and we define the seeding location where we want our particles to be released. And we have two different ways here in the script. You can basically choose which one you would like. One would be to use the discharge transact shapefile that you produced before when you extracted when you created the model in ANUGA. And that will mean that your release point will be at the top of your domain where your discharge is defined. And then all the particles will just be routed into the system. Another way is to use a map. So if you decide to do this, you have to import the shapefile and then translate your points into a list, because that's what this command means, because that's what Dorado needs. And then we also interpolate our seeding locations from our ANUGA grid onto the Dorado grid. So up there, we still have the coordinates of the ANUGA grid. And here we create the indices of our seeding locations on the Dorado grid with this coord to int. That's one way. The other way would be to use the map. And I think that's this one. So that's basically what you've seen already before. Here's our map, and this is the shapefile file that we've been using. So if you zoom in here, you have, this is my example. For you, it probably looks different, but basically you should see here your shapefile that you produced before on this map, and then you can use the marker to define a point of release. So if you take this, you can put it in here somewhere where you want to. You can also have several points if you want to. And once you're done, you save the points to a shapefile, and it will be saved in your folder. And so that's similar to just using the discharge transact, but now we also have to interpolate again on our grid of Dorado. So that's what it's happening here. We have to transform our seeding locations into our seed indices. Oh yeah, it prints the seedling locations. It doesn't print the indices. Just to illustrate, sorry, I'm slow because I have just one hand. So that's just to illustrate, these were the coordinates on your ANUGA grid. And so these are the indices of your Dorado grid, just to visualize what we just did. And then we can plot and see if that makes sense. And that was what we wanted. So basically here we have our shapefile on the new Dorado grid. So the bathymetry cut to our polygon, and then here we have our seeding location. And also this figure will be stored in our output file. So if you wanted to use this, then you will find that figure in your output file. Did everybody get there so far? Does it look good? Any questions? Yes. Mm.
So you need, first
Here?
cells. Where you define all the
I hear you mean.
the next. Here, you see how it's like model data. Yes. So at the end you can get rid of the collab. It's using the collab data.
Mm.
And change the SWW name to whatever is the output finding that you want to use. Okay. But it's not output. Okay. So you said change the SWW, right?
The name. So the problem was that the default data was loaded in. So this is kind of pointing us to the directory where our default data is, which is the data we prepared for everybody who couldn't make their model work or didn't want to use their model output. So if you get the default data here, you have to change the path to where you have your actual shapefile. And also the name of your SWW file might be different in your simulation that you did here to this one. So then you would need to update the name here to load in your actual output file. Is everybody happy with the progress? Any questions? Usually when there's no reaction, that's not a good sign. Here you mean? Sorry, I'm not sure I understood the question. Mm-hmm. Mm-hmm. This cell. Okay. These are the ones I picked from the map. And you're saying if you did the other option, they would have different names? Oh, okay. So I added this this line I added just now. So that might not be there. Oh. Does everybody have the problem that these lines are missing here, these last three? From the top one. Okay. Yeah, so in the top one, oh, yes. So basically you would have you would have a different cell. Okay. So the confusion was that if you did the map, you would transfer your coordinates into indices, but not if you use the transect. So that's why I'm copying now these lines into another cell. So you use them regardless of which option you chose. Thank you. That's excellent. Thank you so much. Mm-hmm. Which file path? This one? This one? This name? Oh, okay. Yeah, I use the default. Okay, so there's another troubleshoot, which is the name of the shapefile of your domain. I use the default one, which is dxws domain. If your shapefile that you produced in your simulation has a different name, you also need to change the name here. And that's at the very top of the simulations. After the window where you define the theta, the next one you load in your shapefile for your domain. And that might have a different name here for you. Then you would need to change that. Otherwise, you load in the default shapefile, which might mess up things. So how's everybody feeling? Can you give me like a thumb, like this is going amazing, I'm already way ahead and already finished everything. This is like I'm still at the top of the script, and medium, I'm like almost there, I need a second. Okay, 1 second, or you're way ahead. Okay, you have a question? Yeah. Yeah, that's because you seed particles every time step. So you actually add particles each time step. And so the next time step, you have twice the particles and 3 times the particles, etc. And that slows down your simulation. Exactly, because you keep seeding. But this an hour 80. Ow. Yeah. How many particles did you seed? Oh, yeah. So because then in each starting location, you will seed the particles. And then next time step, you will again seed in all starting locations the next particles. Yeah, no, that's all right. But if you do that, I would recommend you reduce your number of particles, maybe to 5 or something, or 2, just to see if it gets finished. Yeah, you can, yeah. Okay, but that tells me that some people are actually way ahead, because we were still at transforming our seed indices. So I'm going to move forward. So we did our indices. Now we define our model parameters. And here you can see that our model parameters class has all these different options. So the grid size we defined up there to 25 meters. We have the theta. And here you can actually specify the gamma that we use in our first equation. We have a dry depth, which is basically the water depth that's needed to define if a cell is dry or wet, which is 1 centimeter here. We have the diffusion coefficient, and we add our bathymetry on the name of our file, which is ANUGA. So if we run the cell, we instantiate our parameters class. And so it just, so the final step would be to define when we're actually going to seed. So I'm just plotting here, just out of interest, the times that are saved in our output file. So these are actually the times that we can seed. And those are in seconds. So you can see that there is an interval of 3,600 seconds. So you can seed in all of these, which we're going to do in a second, but you could also calculate larger intervals here if you wanted to. And so those things we define in our next window here. So we have a total number of 24 time steps, and we seed 5 particles per seeding event, which is very low. This is because I initially also had several seeding locations. So if you just have one seeding location, you can actually increase this here to a larger number, let's say 25. And then we create a vector with our target times, which is basically the iteration time that we have. So basically we update our flow field all of these times. You can see that's the same as the time steps that are saved in our output. So every output interval, we actually seed our particles. And so basically that's what we did. And here's our main loop for our simulation run. And there are several things happening here. So first of all, we loop over our list of time steps, which is the 24 time steps that we decided to loop on. Here, we then interpolate our flow field onto our Dorado grid. And that is what I was talking about earlier, that because it's unstructured, it's unsteady, we now have to update our flow field every time step. That's what's happening here. This command will then instantiate our particles that we defined up here before under our params variable. And then we have some time tracking. And then here we actually generate particles using the generate particles function, where we have the number of particles and the seeding locations. And then this is important that we have previous walk data, which means that we actually include the walk data from our previous time steps also in the next time step. So we keep the particles. And the run iteration function is, or command is the main run of our simulation. So if you remember in the first example with a steady flow, we used another wrapper that's called steady plot, which is like a high-level routine that makes it easy to run. But this steady plot will call the run iteration function. So here we basically go one layer deeper in our code and we call this function directly. And then this is a plotting function that will plot our output file and save them in our directory. And at the end of the simulation, we will save our entire walk data in our directory as a text file. So if you got here, you can just run this and it will give you the simulation time here. And so you know how long it will take to run the simulation. Did everybody get here more or less? Thanks. Okay, so my simulation is finished. I don't know about yours, but you can find the output data in the output folder here under our theta. And so if you wanted to run a different simulation with a different theta, you can do so, and then it will be a second folder here. And basically here we have the map where we have our seeding points saved, and then we have our output data. So you can plot and follow the particles. For me, it looks a bit funny now, but that might have to do with the path. But you can inspect here your particle path to see if everything makes sense. Oh, that's never good. Okay, so now we did our simulation. We did an animation in the previous example. We don't do that here, but you could do that. You could add a cell here and just animate your plots. But so now we're going to do a bit of post-processing. And one of the things is to actually calculate the nourishment area, which is what I showed in one of the examples, the number of particles that enter a certain area. So to see actually where the particles are going, relatively speaking. And it doesn't crash, so that's great. And that's like a function that's called nourishment area, which is also provided in the particle track package or wrapper. And so then for this, you just need the walk data, and you need some type, the shape of your grid. And sigma is, I believe that's a smoothing factor to smooth your output. And then you get a map that looks more or less like this. Sorry, it's not showing very well on my screen, but basically you can see, you can see that the particles are going in the main channel, and some of them, they are leaving the main channel and then go over the floodplain. And basically the color scheme means that the darker colors is where most of the particles are going, so close to 1. And then the lighter the colors, the less particle are going. No, exactly. That doesn't mean there's deposition or anything. That is just to visualize the nourishment of the domain with particles. So the number of particles entering the domain. And so in addition to the nourishment area, we can also look at the nourishment time that we've been looking at before. So how much time do particles actually spend in parts of the domain? Because just because they're going there doesn't mean that they're also a long time there. So they might just flush through, or they hang out there forever. So we can visualize this also as a map using the function nourishment time, which is very similar to nourishment area, just that you now compute time. So if you do that, you get a similar map, different colors, and then you have the mean nourishment time in seconds as a color bar here. And you can see that where most of the particles go, they also go through the channels really fast, which is what you expect. Most of the water would just go through the main channel. And then you have areas on the floodplain where the particles will be a little longer, especially in this area. So there are these ways to visualize qualitatively where your particles are going, but you might want to also do this quantitatively, that we do in a second. Just as a side here, we did the travel path plot, in the previous example, and we can do it here again, which is the drop path, travel path function, and then it will give you, for the IDs that you define, I define here ID 0 to 9. It will give you the different paths of the particles. Everybody still with me? Excellent. And so the final step will be to quantify the exposure time of an aggregate to particles. So basically what we've been showing, seen in one of the examples in Lake Pontchartrain, where Katie plotted the exposure times of particles depending on the flushing setup of the spillway, if you remember. And so in order to do that, you basically have to define a region of interest, a region of interest, RI, that you want to look at. So that you want to have an area where you want to see how many particles are actually going there and how long are they there. So there are different, feel free to change this if you feel confident to use Python, if you have some specific question. But what we did here is we actually try to get the higher elevations of our area. So we define a function that extracts these areas that are above bathymetry above 0 meters, which is just a threshold that I put here. I'm usually interested in wetlands, so I would look at where are the wetlands. You could also use the friction map with the different vegetation classes to look at different vegetation types and how many particles go into each of these areas. So you could adjust this. But so I look at these higher elevations. So basically I define an ROI, And then I compare the topography, and everything that is below 0, I will set to 0. So what you need for the ROI is a binary map where you have ones and zeros, and everything that's 1 will be included into your analysis, and everything that's 0 is excluded. And so, so this will be the area that I will investigate. And to calculate exposure time, there is a function called exposure time. You see, it's very intuitive, but you have your walk data that we saved at the end of our simulation when the loop finished. We have our region of interest, and then it will calculate the exposure times. Sorry. And so it will give you a list of the coordinates of the coordinates of your region of interest, and the indices of the particles and their time that they spent there. And so you can calculate a function. You can use that calculated exposure time to then plot it with a function called plot exposure time. And so here, this will give you a cumulative exposure time distribution, similar to what we've seen with Katie's plots. So here we have the time that particles spend in that area, and you can see that they basically entered the area and then they kind of leave. So so you can use this exposure time distribution function to then assess how the particles, how much time they actually spend in an area and when they leave. Everybody still with me? Okay, great. So if you have done this and it all worked, then I encourage you to change your theta and do some test runs. So you could either change your theta, then it will always create a new folder. So that's easy to keep all the results there and don't overwrite them. You could also change your seeding locations or the number of particles you want to seed and see how that changes your results. But if you don't change your theta, your results will be overwritten. So either you also change the theta, or you can basically create a new folder using the command here, a new subfolder, sorry, not this command, this command here, so where we create our output folder. So you could copy that lower in the script and make a new folder every time you change the number of particles, for example, or the number of seeding locations. So if there are no more questions, then I just encourage you to do that. And if there are any questions, we're here.
Maximum, right? And you said because the particle goes away, but doesn't that mean it just stays there? Because once it's above, say, half an hour.
Yeah, so that's the distribution function. So basically you have a particle entering the area and then they kind of disappear.
Yeah, okay, it doesn't accumulate anymore because it's not there anymore.
Yeah, exactly. And that's because I have very few particles. Actually, it's too little to do this distribution. That's a good point, actually. So just as a side note, to get the exposure time distribution, it will give you a warning if you don't have enough particles or enough iterations. I use very few particles here. So if you want to have a significant result from this plot, then you should probably run quite a few particles. Yeah, here it says at least 1,000. I don't think it's feasible to run 1,000 particles now for this here, but just as a note for future reference.